Math 2415, Calculus 3, Section 13.5, Curl and Divergence, video 3 of 6. In the previous video, we showed that the curl of the gradient of a vector is always the zero vector. And as a consequence, we came up with a pretty handy theorem that says if the curl of a vector field is not zero, the zero vector, then the vector field is not conservative. But as we discussed in class last week, we're more interested in things that conclude F is conservative, not things that conclude with F is not conservative, and not things that begin with F if F is conservative. We want things that conclude with then F is conservative. And it's natural to ask that if a non-zero curl implies not conservative, does that mean that a zero curl implies conservative? Which is why I have a question mark here. And the answer is not always, but most of the time, yes. In general, if F is a vector field in R3, and I keep saying in R3, and when you're talking about cross products, you normally assume R3. You can apply cross products to R2 by simply appending a third component of 0 on an R2 vector. Then you're just saying, I'm a vector on a plane, but the plane's in space, and my z component is 0. But if F is a vector field on R3, and its component functions, because remember, F is a function that says, give me a point, I'll give you a vector, so you have a component function for each component. And the component functions, and its component functions have continuous partial derivatives. Imagine that, we need continuity. You see continuity so often in calculus, and you just kind of just assume, well, it's because it's nice and neat. But for those of you heading towards analysis, both real and complex, you'll see why continuity is really so crucial. And the curl is equal to 0, the zero vector. Then F is conservative. So we do have a theorem that allows us to conclude that F is a conservative vector field. The hypothesis of that theorem, antecedent, if you really want to use the correct symbolic logic term, but the hypothesis isn't just that the curl is 0, you have to put and the partials are continuous. I'll admit, I don't know off the top of my head right now if they can just be continuous on a closed disk or an open disk or a connected disk or a simply connected disk. I would have to review a little bit more. But for now, let's just say that if they're continuous everywhere, then a zero curl does imply conservative. So now we have another tool that answers the question, are you conservative? One was in R2 when we compared the partial of P with respect to Y to the partial of Q with respect to X, because Clairaut's theorem said, yeah, that will give us a conservative vector field. But in R3, it's a little trickier. So we have curl to answer that for us now. For example, let's take the vector field f of x, y, z is equal to y squared z cubed in the first component. And the second component, 2xyz cubed, yes, 2xyz cubed, and 3xy squared z squared in the third component. Let me make sure I've got these written down correctly. Y squared z cubed, 2xyz cubed, 3xy squared z squared. All right. Question, is this conservative? Or we're going to push it one step further? If so, find its potential. Now you probably know it's going to be conservative, otherwise I wouldn't get to demonstrate finding its potential. But remember that the fundamental theorem of line integrals basically says that you can evaluate the line integral of a gradient if you know the potential, which is why it's important to answer the question, are you conservative? And if you are, what's your potential? So let's start by showing this is conservative by finding the curl. To find the curl, we're just going to find the cross product of, in fact, let's go ahead and get it set up. We want the cross product of the del operator vector with f, and since I already have f here, I'm just going to write the del operator vector above it, partial x, partial y, partial z. And now I'm ready to find my determinants. I may need some more space here. We'll see. Okay, for the first component, we cover up the first components and find the determinant, in this case, the difference of partial derivatives. Main diagonal, partial derivative of 3xy squared z squared with respect to y. We bring down the 2, 6xy z squared. 6xy z squared. Minus the other partial derivative of 2xy z cubed with respect to z. We bring down the 3, lower the z's power. 2 times 3 is 6, xy. Lower the power on the z, we get 6xy z squared. That difference is 0. Off to a good start. For the second component, cover up the second components and do the negative of the determinant, so we'll just do the diagonals in the reverse order. The off diagonal is the partial derivative with respect to z of y squared z cubed. That would be 3y squared z squared. Minus the main diagonal, partial derivative with respect to x of 3xy squared z squared. That would just be 3y squared z squared. So again, that's going to give us 0. 2 down, 1 to go. For the third components vector, we cover up the third components in the two vectors and take the determinant, so it's a difference of partial derivatives. Main diagonal, partial derivative with respect to x of 2xyz cubed is just 2yz cubed. Minus the other diagonal, partial derivative with respect to y of y squared z cubed is 2yz cubed. And would you look at that, everything zeroes out and we get the 0 vector. Since the curl is 0, and since our partial derivatives are continuous everywhere, they're polynomials, they were destined to be, then we can conclude that f is conservative. And now for the fun part. I did not get to demonstrate this in class, recovering the potential for a conservative vector field in 3 dimensions. We did one for 2 dimensions. It's the same premise. You chase around the derivatives and antiderivatives, remembering who's a constant and who's not. We're claiming, well, we're not claiming, we know that since f is conservative, its first component, which is here, is some function's partial derivative with respect to x. Its second component is some scalar field's partial derivative with respect to y. And its third component is some scalar field's partial derivative with respect to z. So we're just going to chase things around, starting with the first component function of f. We know that the partial derivative of f, of the scalar field, with respect to x is equal to yz cubed. Well, this is a pretty easy one to undifferentiate. If we integrate that with respect to x, then we integrate y squared z cubed with respect to x, remembering that y and z are constant relative to x. It would just be x times this plus something unknown. So xy squared z cubed. But the unknown isn't just a constant number, because y's and z's could have disappeared upon partial differentiation with respect to x. That means that this unknown constant is not just a constant, but it's a function. So we'll say it's a function g of both y and z. As long as it didn't have any x's, it would have completely disappeared upon partial differentiation with respect to x. Okay, so we're x squared plus y squared plus z cubed plus something with some y's and z's. I get the funny feeling that something is 0, but we'll find out. Now that we know that this is what our scalar field looks like, f of x, y, z, now that we know this, now let's take the partial with respect to y. So partial with respect to y. The partial derivative of f with respect to y is the partial of this with respect to y. The partial of xy squared z cubed with respect to y is 2xyz cubed plus the partial derivative of g with respect to y. And because it contains y's and z's, I do have to put partial with respect to y. But we also know that the partial with respect to y of f is supposed to be 2xyz cubed. So this is from what we know about f so far, and this is from the fact that f was conservative, so its second component was the partial derivative with respect to y of something. Well, the 2xyz cubes match, so if we subtract them from both sides, we get g of y is equal to yz. I'm sorry, g of partial derivative of g with respect to y of yz is equal to 0. So upon integration with respect to y, and I'll just put integral dy over here as an indication that that's what we're doing, this will take us back to the g function of yz, and the integral of 0 with respect to y is just a constant, but not a constant function, because what else would have disappeared upon partial differentiation with respect to y? Anything that had only z's and x's, but this guy never had x's. Remember, he showed up from integrating x's partially, and so he never had any x's to begin with. So this is some function of z, we'll just call it h of z. Because upon partial differentiation with respect to y, it would disappear. And it may include a constant, and it may include some z's. So this means that we now know that our original scalar function, f of x, y, z, is equal to xy squared z cubed plus, now our unknown function is just an unknown function of z. We've already taken care of the x's and y's. One more partial derivative with respect to z and we'll have it. If we take our partial derivative with respect to z, we'll know that the partial of f with respect to z is the partial of this with respect to z, which is 3xy squared z squared, plus the partial derivative of this function with respect to z. But this function is function of z only, so its partial derivative is its ordinary derivative. But we also know that the partial derivative of f with respect to z had to be the third component of f. So that's equal to 3xy squared z squared. And I gotta admit, I'm a little bit disappointed that my constant actually is just gonna be a constant. Because if I subtract 3xy squared z squared from both sides, I get the derivative of h with respect to z is equal to 0. Remember, it was a function of z and z only, so upon integration with respect to z, we won't pick up any x's or y's. H of z was some constant, we'll just call it c, and therefore our potential is f of xyz is equal to xy squared z cubed plus a legitimate constant c, a number. Like I said, I'm a little bit disappointed that the constant at every level never amounted to anything except a true constant at the end. I really would have liked to see the g function or the h function have something a little more substantial. All right, so to summarize this video, we now have a tool for answering, is a vector field in R3 conservative? And the answer is, if its partial derivatives are continuous, then if its kernel is 0, that implies it's conservative. That's a handy thing to have, especially if you're trying to evaluate the line integral of a vector field and you would like for it to be conservative.